Okay, coming to the problem section. Okay, so in the last class we studied about what you mean by minimum potential energy and what is the importance of minimum potential energy. Okay, now in today class we will going to solve some numerical problems on concept of what the minimum potential energy. Okay, so here we are going to solve two numerical problems. So what that is what based on that what minimum potential energy method. Okay, so I told you what you mean by minimum potential energy. So same, it is what the summation of, or it is the sum of strain energy plus work potential is called as strain energy. Okay, where strain energy is equal to what the internal forces, that is that will be stored in the internal system, and the work potential is nothing but what the external forces which will act on the given mechanism. Okay, so that is called as work potential. Combination of those two we are going to call as principle of this what the minimum potential this what potential energy. Okay, in the module 1 we are having the three numerical problem, that is three different types of numerical problem. Okay, first one is the type 1, that is problem that belongs to the concept of this what the minimum potential energy, and second one is the type 2 problem, that is a Rayleigh-Ridge method, it is shortly called as a RR method. Okay, and type 3 method is called as what a Gall-Current method. Okay, all these three topics are very important to solve the problems. Okay, that is what to get the what these two these any type of problem may appear in the examination. Okay, so here in the today class we studied we will solve the some numerical problems on type 1 problem, that is minimum potential energy method. Okay, look at this. So before reading this question, so let me understand what once again that is what I mean by potential energy. Okay, so I told you potential energy is nothing but what it is a combination, or it is a sum of strain energy plus work potential. Okay, potential energy is denoted by what capital pi, that we have to remember this equation. Okay, to solve this type of numerical problems, first we have to derive the strain energy on the system, that is a given system, and total work potential on the given system, then combine you are going to get the potential energy. Okay, so that is denoted by what pi. So you have to derive the pi equation, then you apply the boundary condition, then finally you are going to apply the minimum potential boundary condition, so you are going to get the final displacement, that is unknown displacement, they what they asked in the question. Okay, so this is about the procedure for solving the minimum potential energy. Okay, so here they given question like this. Okay, I will read the question now. Number 1, that is the problem number 1. So based on what minimum potential energy. Okay, so here for the spring system shown in the below figure, using the principle of minimum potential energy, determine the nodal displacement. Okay, so take the force F1 is equal to 75 Newton and F2 is equal to 100 Newton. Okay, so here there will be two forces are given. Okay, that is what one force is here, they given F1 is equal to here, and one more force is F2 is equal to here. Okay, so here the spring mechanism is given. So how many springs are there? Here three springs are connected. Okay, the K1 and K2 are connected in a series. Okay, that is what they are connected in parallel. Okay, and here one in between these two one for spring is there. Okay, so K1, K stands for stiffness, that is what stiffness of the mat spring, and D delta stands for deflection, and U we are going to consider as a displacement. Okay, so displacement at node number 1, displacement at node number U2, that is U2. Okay, so here stiffness is given for spring 1 50 Newton per mm, and K2 is equal to 60 Newton per mm. Okay, and K3 is equal to what 70 Newton per mm. Okay, these three spring stiffness are given. Okay, so you need to calculate what the unknown displacement, they are asking determine the nodal displacement. So here how many displacements are there? U1 and U2. Okay, so before solving this problem, let me understand deflection, that is what the delta 1 is equal to what you are going to consider, and delta 2 is equal to what you are going to consider, and delta 3 is equal to what. Okay, so here the force is given F1 here. Suppose look at this diagram, so one external force is acting on this. Okay, if you apply force here F1, okay, both the spring will displace, some deformation takes place here, that is what delta 1 which is equal to U1 which is equal to delta 2. This is very important. Okay, so I will repeat again. If you stretch here the at node number 2, so here deformation takes place. Okay, of the both the spring delta 1 and delta 2. Okay, what you mean by elastic body before? Okay, so elastic body is nothing but what, if you apply a force there will be stretch. Okay, if you remove the force it will come original position, that is called as elastic body. Okay, delta 1 is equal to, if you remove here, if you just apply delta 1 will displace, that is delta 1 is equal to displacement U1, delta 2 is equal to U1. Okay, so here where here also F2 is applying at node number 2, if you apply here force, so here displacement this what K3 spring also displacement takes place, and here also takes place. Okay, that is what delta 3 is equal to what U2 minus U1. Okay, so that we have to assume in this is very important. Okay, if you know that, means you are going to understand, if you are going to solve numerical on easily to solve this type of problem. Okay, so now same, so we know that what the potential energy function is equal to what strain energy plus work potential. Okay, so potential energy of the function is denoted by pi, and which is same right down here, strain energy plus work potential. Okay, so normally we know the standard formula for strain energy of the spring is equal to what half of K into delta square, because this is a standard formula for spring, that is a store energy, that is a strain energy of the spring. Okay, but here three springs are given, so the total strain energy on the spring is equal to add all these things. Okay, strain energy is equal to what, half of k1 delta 1 whole square, wherever is k1 is there, put it 2 3. Okay, half of k1 delta 1 square plus half of k2 delta square plus half of 2 k3 delta 3 square. Okay, so this is the total strain energy acting on this given spring mechanism. Okay, but we know that delta 1 is equal to what, u1, so delta 2 is also u1, delta 3 is equal to u2 minus u1. How we got this? If you apply force here, so delta 1 will displace, delta 2 which will displace at what, they given u1, so hence we are going to consider here delta 1 is equal to u1, delta 2 is equal to u1. Okay, similarly come to this, if you apply force here, here displacement and here displacement takes place, that is u2 minus u1, so right here delta 3 is equal to u2 minus u1. Okay, so this again you substitute in the above equation, so the total energy on the system we have, that is what, half of k1 delta 1 in place of delta 1 u1 square plus half of k2 delta 2 is equal to u1 whole square plus half of k3 u3 minus u1. Just substitute all the delta values in this above equation, so you are going to get the total strain energy on the particular given spring that is a spring system. Okay, so now you calculated this, again go for calculating the work potential of the system. Okay, so work potential of the system is equal to what, so we have the two external forces. Okay, so here two forces are acting. Okay, so here that is what, force 1 force 2, so f1 into displacement, that is force of f1 into u1 minus f2 into u2. So here let me understand here, so here if the force acting on the system is considered as positive, if the work done by the system going to consider by negative sign, so here work done by the system is minus there, so we are going to consider the negative sign. Okay, minus f1 or u1 plus f2 u2, if you take the bracket means plus, if you remove the bracket means both the signs are negative. Okay, so now once you calculated the work potential and the strain energy on the given system, then you substitute these two equation in the potential energy equation, that is the first equations. Okay, so if you substitute here, again pi is equal to half of, if you substitute there, you are going to get like this. Okay, so this equation is a1 minus a minus b whole square. Okay, so just you resolve this, a square plus b square minus 2ab, so you are going to get this again strain energy, this is the work potential, this is the strain energy. Okay, so again you resimplify this, so total potential energy of the function is equal to what, pi is equal to half of u1 whole square. So here q1 is if you take common, u1 is equal to k1 plus k2 plus k3 plus u2 whole square k3, just you multiply these two. Okay, so u2 k3 u2 square minus 2 u1 u2 k3 minus of f1 u1 minus f2 u2. Okay, so this is the total potential energy function, but our aim is to what, to find the unknown displacement. Here unknown displacement is equal to u1 and u2. So look at in this diagram potential energy function, so u1 and u2 are the two unknowns are there. So if the potential energy function is to be minimum, so condition is you just differentiate with respect to u1 and differentiate with respect to u2, that is this is a condition. Okay, so dou pi by dou u1 which is equal to 0 and dou pi by dou u2 which is equal to 0. So this is a deflection, that is a what, this is a condition for potential energy to be minimum. Okay, so now differentiate this equation with respect to u1, so you are going to get what, dou pi by dou u1 is equal to half of 2 u1 into k1 plus k2 plus k3 minus 2 u2 k3 bracket close minus f1 which is equal to 0. Okay, again this dou pi by dou u1, this goes this direction, so that becomes 0. So we want the force f1 is equal to, so this take the 2 common, this 2 to get going to cancel, so finally you are going to get final equation this. So f1 is equal to u1 k1 plus u1 k2 plus u1 k3 minus u2 k3. So give equation number 1. Okay, so similarly calculate differentiate with respect to potential energy function with respect to u2, so that is dou pi by dou u2. So differentiate this equation with respect to u2, so we will get dou pi by dou u2 is equal to half of 2 u2 k3 minus 2 u1 k3 bracket close minus f2. Okay, this again goes to that side, so it becomes 0. So f2 is equal to minus u1 k3 plus u2 k3. So okay, now we will understand this equation from the equation number 4 1 and 2. So solving the equation 4 and this b and c, you can denote any one, 2 3 4 5. Okay, so if you simplify this equation b and c, so you will get u1 is equal to f1 plus f2 whole divided by k1 plus k2. Okay, so force is given 75 Newton in the given question, f2 is equal to also given, spring value is also given k1 and k2. Okay, substitute, you are going to get the displacement at node number 1, that is u1 is equal to 1.59. okay, so that is what, u1 is equal to 1.59 mm. So if you apply force here, so displacement takes place at what, 1.59 mm it will displaced. Okay, so again this value you can substitute here any one of the equations, you are going to get what, u2 is equal to 3.019. Okay, so here displacement at node number 2 is what, 3.09 mm. Okay, so these are the two these are the two displacement we calculated based on the given question. Okay, so that is the total nodal displacement is equal to u1 of 1.59 mm and u2 is equal to 3.019 mm. Okay, so like this you have to solve the numerical problems on based on minimum potential energy. Okay, so I think you understand this problem. Okay, I will repeat again. So here in this case, it is very important to understand this what, how to apply this deflection, how to assume the delta values. That's it. So remaining procedure is same. Okay, delta 1 is equal to, if your node number force is applying here means okay, if you apply means this will be deformation takes place. That is here they given u1, delta 1 is equal to u1 and delta 2 is equal to u1. Okay, same here u2 they given. So here u1 on given. If you apply force here, it will take displacement here and here. Okay, so that is u2 minus u1. Like this you have to solve the numerical problems on potential energy function based on minimum potential energy. Okay, so finally you are going to get the answer. u1 is equal to 1.59 and u2 is equal to 3.09. okay, so I hope you understand the first problems belongs to minimum potential energy. Okay, so thank you.